I'm putting a diagonal just to tell you that you've chosen the diagonal transformation which will diagonalize. Let me also put that u vector somewhere here. U vector for lambda equal to 0, the eigenvector was u equal to 1 minus 1 by root 2 and 1. Okay. So once I put in the diagonal, do the transformation which leads into diagonal form, then you see that then in that case my j prime I will be equal to sigma diagonal. Let's call this as sigma. Ig. Eg. So this then tells me that j prime 1 will be equal to lambda 1 E1 prime. J2 prime will be equal to lambda 2 E2 prime and J3 prime equal to lambda 3 E3. Now when your basis vectors in the diagonal ones are diagonalized, so I've gone to the basis vectors. You can choose the basis vectors then as equal to U1, U2, U3. So this is your diagonal basis. P prime D is equal to this. This is my U3 basis. And let me call it U1. And if you look at this from that matrix, which I've given you for sigma ij, the matrix I gave you just now, the eigenvalues are lambda equal to 1, 4, and 0. Like that. So 0, 1. Okay. This is the eigenvalue. So please solve this. I'll give this again as part of your tutorial, but I'm just telling you. You can already check that the eigenvalues are 0, 1, 4 for that particular matrix. So, given these eigenvalues, or once you find out the eigenvalues, the corresponding eigenvectors are U1, U2, and U3. Please don't confuse this with the components. Maybe I should keep some. So let me call, okay, instead of calling it as U1, let's call it as phi 1, phi 2, phi 3. So let me call this as phi 1 so that you don't confuse with the components of any vector. So the phi 1, phi 2, phi 3, these are the corresponding eigenvectors corresponding to. So corresponding to this you have phi 1, corresponding to this you have phi 2, and corresponding to this you have phi 3. Now these eigenvectors, see in this case what you have, you can also see that if I look at the form of sigma, that's a Hermitian matrix. So the eigenvalues must be real, and you find you have real eigenvalues. And further, what you can also check is that, or you know that if you have a Hermitian matrix and if corresponding to two distinct eigenvalues, the corresponding eigenvectors are orthogonal. In this case, what you find is that you have three distinct real eigenvalues. So all these eigenvectors, phi 1, phi 2, phi 3, must form a set of mutually orthogonal vectors. So this phi 1, phi 2, phi 3 will constitute a basis for your R3. Fine. So what this is now telling you, so this is your prime basis, what I was calling earlier as E1 prime, E2 prime, E3 prime. So what this is now telling me is that since lambda 1 is identically 0, J1 prime equal to 0. Alright? Or in other words, what it tells me is that suppose I put, so if I apply my electric field, so if your electric field E equal to some E1 prime phi 1. So if you apply the electric field along this direction 1 minus 1 by root 2 plus 1 by root 2, then in that case there will be no current flow across the conductor. Because in that case E2 prime and E3 prime are 0, and you're going to get only this, which is going to be 0. So what you can see therefore is that once I write it, this is an example where you actually use a tensor, where you really show that a physical property is described by a tensor of rank 2, a higher order rank 2 tensor. And further that I can use the tensorial properties or use the tensor properties to find out some physical consequences. So it tells me that if I want to conduct electricity through this object, then better not choose this particular direction at all. And if I ask you now, which is the direction in which I must apply the electric field such that I get maximum conductivity, then that tells me that I should use the direction phi 3. So if I apply the electric field along that direction, phi 3, along the vector phi 3, then you will get the maximum conductivity in the material. Right? So this is an illustration, for example, of a place where, as I said, that one can use tensorial properties. So the thing again I want to emphasize, note that firstly I've written down, this is a physical equation of physical law, because it is relating the applied electric field to the current which flows across the conductor. The form of this law itself is a covariant. When I say covariant, I mean it in this particular sense, that the form remains the same irrespective of which coordinate system or which coordinate axis I choose. And that is guaranteed by the fact that the left-hand side, quantities on the left-hand side and on the right-hand side transform in the same way. See, this is more complicated than this kind of an equation. See, because in this case, your M was simply a scalar, and left-hand side was, and right-hand side both you had vectors of F and A. On the other hand, here now I have left-hand side also a vector. Here also I have a vector, but this is getting multiplied by not a scalar but by a quantity which is a tensor. Okay, but I'm still guaranteed form covariance because of the fact that the tensor transforms in this very nice or in this particular transformation, specific transformation properties. If it did not have the kind of transformation properties which the second rank tensor should transform, then what it means is that then this equation doesn't remain the same in these two different coordinate choices, coordinate axis choices. But then that will tell me that my physics is not remaining the same. Because see, this is after all, this is what we call as Ohm's law. Because then it is telling me that I have one kind of an equation if I use one choice of basis, and if I use another rotated basis which is different from that, then I have another kind of physical law. So that really doesn't make much sense. Okay, so this is what I meant by saying that tensors also naturally allow us to talk about what are known as symmetry properties, because you expect that the coordinate choice of coordinate basis should not change my physical laws as such. So I can change the values. For example, I know that if I use for a certain coordinate axis, I can get the acceleration components to be, say, in one particular choice of basis, I can get A1, A2, A3. In another choice of basis, I will get A1 prime, A2 prime, A3 prime. But my Newton's law must remain the same, that the force is proportional to the acceleration and the proportionality coefficient is simply m, which is a mass, and that should be independent of choice basis. So the fact that I have this particular equation F equal to ma, irrespective of choice of basis, that says that my physical laws remain the same. So similarly, if I want this physical law to remain the same, it should be that given that this doesn't transform like now a scalar, then this must transform like a tensor. Okay. So what we will see, I mean later on, in fact, when you do in many equations, as I would, many times what one can do is, if I know like how a certain quantities transform, and if I expect that these laws must hold irrespective of what choice of coordinates I've used, then I can automatically, like for example, I said that this transforms like a vector, this transforms like a vector, and I know that this it's a physical law which must be true in whether I do in this coordinate basis or a rotated coordinate basis, then I can automatically tell you that this must transform like a tensor of rank 2. I have no other choice. And later on, I mean, when you especially do, this is, as I said, this is an after all a solid state kind of or condensed matter physics problem. So in many physical situations, that the form of a certain quantity, that how it transforms, like here, for example, that the conductivity tensor transforms like a scalar, as a tensor of rank 2, is forced on us by simply demanding that my physical law remains the same in two different coordinate systems. So you will find even more general or more interesting applications of such laws or such kind of symmetry properties, which are forced on you simply by demanding that the physics remains the same, irrespective of what coordinate choice I make. See, this is not depending upon whether I've done the experiment and got the sigma matrix or not. It is simply coming from looking at how my law itself must transform in two different bases or two different coordinate bases. Okay. Another very important application of this is in classical mechanics, or actually, in fact, that is where you actually start studying. So let's consider a rigid body. I mean, this is where actually I think you are introduced to tensors very speaking. So if I consider a rigid body, let me just consider. Yeah. So suppose I have now a rigid body which is made of. So this is an example which I'm taking from mechanics. And in fact, I think that this is where you first encounter the idea of second rank or higher order tensors. So let's take, I have a rigid body which is made of particles. Of say n particles, okay? And point particles instead. So, and let us say that, so let's say that each of these point particles have mass, different masses, n, and I'm going to label the particles by this alpha, which is 1 to n. So essentially it's like this, but let me choose some coordinate origin, and let us say that I have a certain set of axes, and with respect to this, let's say that this is my M1, particle 1 with mass n. Then let us say that this is particle 2 with mass M2. This is particle M3. So suppose I have 3 particles. And let us say that with respect to this particular choice of origin and particular choice of axis, they are located at this position, and this position. So if there are 3 particles, then I have these. So this will be like R1. This will be R2. And this is going to be R3. So this is R3 here according to me, and this is going to be R2. Okay. So if I have, say, a system which is made of, so you can imagine this to be some light rods, and you have these point particles, each of which is mass. So I can think of this whole collection as some kind of a rigid body. Right? And now let me say that I'm not restricting myself to just 3 particles. I'm saying that I have more than 3 particles. Let's say most generally I have up to some n number of particles. And I'm also denoting the position vector of the ith particle. So mass of the ith particle is, mass of the alpha particle is M alpha. I'm denoting it like this, and position of the ith vector of the alpha particle. So this is with respect to assert to the O and choice of coordinate axis. So some particular choice I made of the coordinates. So this is my ijk axis, and with respect to this and with respect to this origin, I have this. Now imagine that I'm going to rotate. So I have this collection. So for simplicity, you just take 3 particles, M1, M2, M3. Now imagine that I'm going to rotate this. So I now think that I have some axis like this. So let us say that this is some axis which is along an n cap direction. So along this direction, what I'm going to do is I'm going to rotate this whole collection of particles by some angular velocity omega. All right. So I rotate this rigid body by an angle omega through some axis. Okay. So suppose I rotate. Okay. So you rotate the rotate. I'm writing it all because this is angular frequency omega. about an axis n. That means about that direction. So if this is my n cap, so I rotate this full rigid body. So it's basically, you think of this as some collection of point particles which I have connected by rods, and then I take that full assembly of particles and rotate the full thing by some angular frequency omega about some particular axis, which is denoted by n. So now I can ask you, what is the angular momentum? So now my question to you is that, what is the angular momentum now about this assembly of particles? Suppose I take just one particle. Let's say I choose just the first particle. What will be the angular momentum? Because say I'm now rotating it, this rigid body, by some angular frequency. So what will be the angular momentum of this system? Suppose I have just one particle. What will be the angular momentum? What is angular momentum by definition? And also, please, I want you to that whenever we talk of angular momentum, it's with respect to a particular choice of origin. So about this choice of origin. Suppose I have a point particle, and what will be the angular momentum for that particular particle by definition? About a certain choice of origin.
R cross P.
R cross P, very good. Wait, what is R? So please remember, whenever I talk of angular momentum, we talk of R cross P. R is a position vector. So whenever I'm talking about position vector, it is with respect to some choice of origin. So here I'm going to talk with respect to the origin which I've chosen. So if I have one particle, I have this. And what? So R is a position vector with respect to the origin. What is this P here? In your definition of angular momentum, what is P?
Linear momentum.
Linear momentum. Very good. Correct. Okay. Now I have this system. So imagine just that I have one rod here. Okay. And I have this. And I'm rotating that by some frequency. So what will be the momentum then? Okay. Momentum, how is it defined? Correct. Please, for linear momentum, how is linear momentum defined for a particular mass L?
Mass into velocity.
Very good. Mass into velocity. Okay. Now your velocity is, this particle is just rotating. So imagine that I have this rod here and it is just rotating with some angular frequency omega. So what should its velocity be? What should its velocity be?
R cross omega.
Pardon? Yeah.
R cross omega.
Omega cross R.
It will be omega cross R. That is the way it comes. Right? So in this case, therefore, now, so now I have here for each particle, therefore, I can write the angular momentum as, so I can say for each particle, the angular momentum will be R alpha cross P alpha. And that's going to be therefore R alpha cross M alpha, because momentum is this, times V alpha. Or I'm going to write this as equal to, so for the alpha particle, I'm going to get the angular momentum as this, M cross R cross V alpha. But because I've rotated this about this axis, this thing, now omega I've written this about the axis n cap. Now I can write this omega, I'll define this like this. Okay. So I can define the vector omega as n cap times omega. And then you can see that this is like nothing but R alpha cross omega cross. Okay. So this should be the angular momentum for the alpha part. This is very simple because V will be simply nothing but dr by dt. So dr by dt will be simply omega cross R. That's all, because you only have a rotation. So obviously then the total angular momentum will be the angular momentum for, you just sum up over the angular momentum for all of it. So if I take the total angular momentum, this simply should be alpha equal to 1 to n. So this should be alpha equal to 1 to n. and it should be alpha equal to 1 to n. Okay. Now you will see the interest in writing this. So you can see that I have this m alpha and then I have this r alpha with the cross product of omega cross r. Okay, so now if I use all our vector notations, so this whole thing, notice that this left hand side is a vector. So the ith component then, I'm removing this, I'm actually, part of my board has gone away, but anyway. So if I look at the ith component of the angular momentum, I won't use J, I will use K. Li will be, now you can see that because I can use all this technology which I've done, this is a cross product. So the ith component I can simply write in the following way. Epsilon ijk. This is like your A and this is like your B. So I will get x alpha j and then the ith component of this object. Okay. And just if you remember earlier, omega cross r alpha k, I can use epsilons. So if I take this part, let me just simplify this for you first. So your r alpha cross omega cross r alpha. If I look at the ith component of this object, it will be epsilon ijk xj alpha times omega cross. See, this is again same thing which we did a little bit earlier in the morning or earlier in the class today. And this again I can write it as epsilon ijk. Now the kth component of this cross product can be written as kln xj alpha omega l and xn. By omega l I mean this. So this I can write it as equal to omega times n1 cap I cap plus omega times n2 cap j cap plus omega n3 cap k. So this is omega 1 will be omega n1 cap, omega n2 cap, and omega n3 cap, where n cap dot n cap equal to 1. And n1 cap, n2 cap, n3 cap are the components of this axis along which or about which you are doing the rotations. And so again, now you use the same identities which we have had earlier. So I'm not doing it elaborately because we have done this just in the morning. So what you will find is when ILJM, so this tells me that L should be equal to I, so I'm going to get then an omega I times, and J should be the same. So from the first part, you're simply going to get xj alpha xj alpha from this first term, and from the second term, what you're going to get I should be equal to M, and J should be equal to L. So I'm going to get xj alpha omega J, and then I'm going to get an xi alpha. Okay. Now, what is xj alpha, xj alpha? Can you tell me what is that? Okay, maybe I will just write it here and then we will write. So, after simplifying this whole thing, what I can do is, let's write it here and then I'll see. I can write my angular momentum, the ith component of the angular momentum, as Li equal to sigma alpha equal to 1 to n. So, basically, I'm just summing over all the different angular momentums. And I can write it as m alpha times this expression. So I have omega I xj alpha minus of xj alpha omega j xi alpha. Okay. All right. Now, what is xj alpha, xj alpha? What will that be? Forget the alpha label. See, alpha label is simply for the alpha particle. So if I just take xj, what is the answer?
x1 square x plus x2 square plus x3 square.
So what is x1 square plus x2 square plus x3 square?
R square.
Mod
R square. So it is R square for the alpha particle. Because R alpha is the position for the alpha particle. So therefore what you can see is that this simply is going to give me alpha equal to 1 m alpha. So the first term is simply going to be omega I, and you will get R alpha square from here. And this one I'm going to write it as xij alpha omega j. Okay. The second term, I just put xi here. It doesn't matter because these are real numbers, I can commute them. Now I'm going to do a little bit more manipulation and write this in the following way. So this omega I write here the first term, let me write this. So it's R alpha square omega j into delta I. So for omega I, what I've written is omega j. So the first thing I've done is I've replaced this with this. Okay, people might get confused, so I put it ij here. Replace this xj alpha with R alpha square, and then omega I have written as omega k into delta I k, because I know that this is going to be 0 unless I equal to k. Okay, and here also if you like I'll put k here. Because it's a dummy index, I'll put this as k. Fine. So now you can see what I can do is I can take the omega k outside of the bracket. Fine. Now, how does this quantity transform? R alpha square. So forget the alpha for the minute. I have R square delta I k minus xi x.
Tensor of rank 2.
So you can see that this is exactly what I introduced a little bit earlier. So let me call this as. So you can see that if I define now I alpha I k, or let me define it as I alpha j k as equal to R alpha square delta j k minus xj alpha xk alpha. This will transform like a tensor of rank 2. Okay. So therefore I can write this as sigma alpha equal to 1 to m alpha I alpha j k, or in this case I got I k. So my angular momentum component along the ith direction can be simply written like this. Okay, by the way, I define with an m also. And also take the m into account. See, the m factor will not make any difference. Why will it not make any difference? I introduced the m also here. Why should it not make any difference? M is the mass. How does mass transform?
It is invariant.
It is a scalar. Okay. So therefore, so I have a second rank tensor multiplied with a 0th rank tensor. So my total angular momentum is simply nothing but I alpha I k times omega. The I component. And also from here you can also see one more thing, that this omega k, because this is simply the angular frequency of rotation. So it is simply the omega times, the kth component is omega times nk, where nk is the unit vector component of the component of the unit vector n cap along the kth direction. It doesn't depend upon alpha. So I can actually finish this summation. And let me call now I jk to be equal to, or should we give a different definition? Okay, let's do this. Ijk alpha. Maybe it's confusing. So let me give us some other name for this. Let me call this as say m rings. So let me call this as sigma alpha equal to 1 to n I alpha j. Okay. See, I can take this omega k out of the alpha summation because it doesn't depend upon which particle, because the frequency is independent of that. And this whole thing, that the summation of I k alpha for all the I alpha n. For all the n particles, that I will call as mjk. So this simply becomes then mjk times, or sorry, mik times. Now you can also say that for each of this, it's transforming like a tensor of rank 1 and tensor of rank 2. So I've summed up over n such tensors of rank 2. So this mjk, how will it transform?
Second rank tensor.
It's the second rank tensor because I've just added up n such tensors. Okay. And this tensor, so now you can see that the ith component of the angular momentum is simply equal to mik omega k. So I've got this equation which is of this form. Li equal to mik omega k. Now you can see from here your angular momentum we have already established is something which transforms like a tensor of rank 1. Omega is nothing, this vector omega is n cap omega. This is simply a scalar quantity. N cap is a unit vector. So this omega bar must transform like, or the vector omega must transform like a vector or a tensor of rank 1. And again, as I said, that you can show then that, okay, in this case now, I know that this M is a second rank tensor. So I've taken a second rank tensor, combined it with the first rank tensor, contracted these two indices. So whatever is the resultant is a tensor of rank 1, which is your angular momentum. So again, you get an equation which is relating the angular frequency to the angular momentum through this second rank tensor object, which is called as the moment of inertia tensor. Or actually, I won't call it moment of inertia tensor. I'll simply call it as the inertia tensor. So this Mij, this is called as the inertia tensor. See, this is very much like our kinetic energy relations, where in kinetic energy what we have is, or if you not kinetic, momentum relation, P equal to mv, or Pi equal to mvi. See, here what it tells me is that the momentum, the linear momentum will depend upon the linear velocity, and the proportionality factor is the mass. So if you have a very large mass, then the linear momentum is very large. If the mass is small, the linear momentum is small. And in the same way here now, what you're saying is that the angular momentum will depend upon your angular frequency. So it's like here the velocity here, I have the angular frequency here, and the proportionality factor in quotes, because it is not now a scalar quantity. Unlike here, where you had a scalar here now it's not a scalar quantity, but this is something which is called as the inertia tensor. But what that inertia tensor will tell you is how susceptible is that rigid body to rotations. Because if you have a large inertia, if m is large, then the angular momentum will be large. If it is small, it will be small. Okay. Okay. Now you can also note one thing. Now from looking at the definition of the inertia tensor, some properties of the inertia tensor we can see.
Excuse me, ma'am.
Yes.
Ma'am, our MCP lecture is going on.
Going on means it has started or it has.
Yes, ma'am. It started 5 minutes ago.
But then you should have told me I would have stopped, right? You cannot have simultaneously 2 lectures, no? So you also have told me then. Okay, so I'll stop here then. We'll continue this tomorrow at 11:30. Is that fine? See, I can't see you people, so you must tell me if your other class is starting. Because how do you allow another class to start like that?